Today we are going to learn operations on convergent sequences. Operations on convergent sequences. Operations on convergent sequences. First operation, that is theorem number 1. Theorem number 1, if Sn and Tn are sequences of real number and limit n tends to infinity of Sn is equal to L, and if limit n tends to infinity of Tn is equal to M, then limit n tends to infinity of Sn plus Tn is equal to L plus M. That is limit of Sn plus limit of Tn. This is the statement of theorem number 1. If sequence Sn n is equal to 1 to infinity and sequence Tn, sequence T suffix n is equal to 1 to infinity are sequences of real number, are sequences of real number. Sequences of real numbers. If limit n tends to infinity of Sn is equal to L, if limit n tends to infinity of T suffix n is equal to M, then limit n tends to infinity of Sn plus Tn is equal to L plus M. Then limit n tends to infinity of Sn plus Tn is equal to L plus M. That is limit of Sn plus limit of Tn. Since by hypothesis Sn and Tn are sequences of real number, proof. Since by hypothesis sequence Sn n is equal to 1 to infinity and sequence Tn n is equal to 1 to infinity are sequences of real number, are sequences of real numbers. Limit n tends to infinity of Sn is equal to L. Since limit n tends to infinity of Sn is equal to L. Therefore, by definition of limit of sequence, by definition of limit of sequence, by definition of limit of sequence, for every given epsilon positive, for every given epsilon positive, epsilon upon 2 is also positive, greater than 0. There exists positive integer n1 or n1 belongs to I, such that modulus of Sn minus L less than epsilon by 2 for all n greater than or equal to n1. Relation 1. Since sequence Sn n is equal to 1 to infinity is convergent to L. Since by hypothesis limit n tends to infinity of Tn is equal to capital M. Therefore, by definition of limit of sequence, limit of sequence for every given epsilon positive, for every given epsilon positive, epsilon by 2 is also greater than 0. There exists positive integer n2. n2 belongs to I, such that modulus of Tn minus capital M is less than epsilon by 2 for all n greater than or equal to n2. This is a relation to. Let capital N is equal to maximum of n1 and n2. Maximum of n1 and n2. Either capital N is greater than or equal to n1 or n is greater than or equal to n2. Then 1, 2 becomes, then 1 and 2 becomes, relation 1, 2 becomes modulus of Sn minus L less than epsilon by 2 for all n greater than or equal to capital N. And 2 becomes modulus of Tn minus M is also less than epsilon by 2 for all n greater than or equal to capital N. This is say 3 and 4. 3 and 4. Now, modulus of Sn plus Tn minus L plus M is equal to modulus of Sn S suffix n minus L minus S suffix n minus L plus T suffix n minus M. And by properties of modulus, mod of A plus B less than or equal to mod of A plus mod of B. Therefore, this LHS is less than or equal to modulus of Sn minus L plus modulus of Tn minus M. Modulus of Sn minus L is strictly less than epsilon by 2 for all n greater than or equal to capital N. And modulus of Tn minus M is also less than epsilon by 2 for all n greater than or equal to capital N. Therefore, each modulus is strictly less than epsilon by 2 plus epsilon by 2 for all small n is greater than or equal to capital N. Epsilon by 2 plus epsilon by 2 becomes epsilon. Modulus of Sn plus Tn minus L plus M is less than epsilon for all n greater than or equal to capital N. Therefore, by definition of limit of sequence, limit n tends to infinity of Sn plus Tn is equal to L plus M. That is, L is limit of Sn and M is limit of Tn is equal to limit n tends to infinity of Sn plus limit n tends to infinity of T suffix n. Hence the proof of theorem, hence the proof of theorem 1, theorem 1, hence the proof of theorem 1. Now we see theorem 2nd. Theorem 2nd. If Sn n is equal to 1 to infinity, sequence Sn n is equal to 1 to infinity is sequence of real number, is sequence of real numbers, sequence of a real number. If C belongs to R, C is a real number, and if limit n tends to infinity of Sn is equal to L, then limit n tends to infinity of C times Sn is equal to Cl. C times Sn is equal to Cl. Proof of this theorem. Proof of this theorem. If C is equal to 0, then theorem is obvious. If C is equal to 0, then theorem is obvious. That is trivially true. If C is equal to 0, then limit n tends to infinity of C times Sn is equal to 0 times Sn is equal to 0, and 0 into L is also equal to 0. Therefore, if C is equal to 0, theorem is trivially true. We assume C is not equal to 0. If C is not equal to 0, that is, C is less than 0 or C is greater than 0, then mod C is always positive, greater than 0. We take epsilon is equal to epsilon upon mod C, which is positive number. Epsilon positive, mod C positive, epsilon upon mod C is positive. We take epsilon is equal to epsilon upon mod C, which is positive number. Since by hypothesis limit n tends to infinity of Sn is equal to L. Therefore, by definition of limit of sequence, by definition of limit of sequence, for given epsilon, for given epsilon is equal to epsilon upon mod C, which is positive. Epsilon upon mod C positive. Epsilon upon mod C positive. There exists positive integer n belongs to I such that modulus of Sn minus L less than epsilon is equal to epsilon upon mod C. Epsilon upon modulus of C. for all small n greater than or equal to capital N. Multiplying by mod C. Multiplying by mod C. We obtain mod C into mod of Sn minus L. Sn minus L less than epsilon for all n greater than or equal to capital N. Mod of AB is equal to mod A into mod B. Therefore, we write modulus of C times Sn minus L is less than epsilon for all n greater than or equal to capital N. Multiplying by C, we obtain modulus of Csn minus C times L is less than epsilon for all n greater than or equal to capital N. Therefore, by definition of limit of sequence, by definition of limit of sequence, limit n tends to infinity of C times Sn is equal to CL. C times Sn is equal to CL. For all C belongs to R. For every C belongs to R. For any C which belongs to R. L is limit of Sn. L is limit of Sn is equal to, we write C times limit n tends to infinity of Sn. Hence the proof of Theorem 2. Hence the proof of Theorem 2. Theorem number 3. Theorem number 3. Number first, if 0 is less than x is less than 1, then sequence x raised to n. Then sequence x to the power n is equal to 1 to infinity, converges to 0. Converges to 0. Second one, if 1 is less than x is less than infinity, then sequence x raised to n is equal to 1 to infinity, diverges to infinity. Diverges to infinity. Diverges to infinity. And third one, if x is equal to 1, then sequence x raised to n is equal to 1 to infinity, converges to 1. Converges to 1. Proof of first result. Proof of first result. Since by hypothesis 0 is less than x is less than 1. 0 is less than x is less than 1. Means x is strictly less than 1. X raised to n plus 1. Now, x to the power n plus 1. X to the power n plus 1 is equal to x raised to n into x raised to 1 for all n belongs to I, for every integer n. And since x is less than 1, therefore this is less than x raised to n. X raised to n. Since x is less than 1. Since x is less than 1. That is, x raised to n plus 1 is less than x raised to n for all n belongs to I. For every positive integer, n belongs to I. That is, x raised to n is greater than x raised to n plus 1 for all n belongs to I. For all n belongs to I. If we put n is equal to 1, we obtain x is greater than x square. If we put n is equal to 2, we obtain x raised to 2 is greater than x raised to 3. And so on. X raised to n is greater than x to the power n plus 1 and so on. Therefore, the sequence x raised to n, sequence x raised to n is equal to 1 to infinity is non-increasing sequence. Non-increasing sequence. X raised to n is equal to 1 to infinity is non-increasing sequence of real numbers. This is statement 1. Since by hypothesis 0 is less than x is less than 1. That is, x is greater than 0. That is, x is strictly greater than 0. Taking nth power on both the sides, x to the power n is greater than 0 for all n belongs to I. Therefore, sequence x raised to n is equal to 1 to infinity is bounded below. Therefore, sequence x raised to n is equal to 1 to infinity is bounded below. This is a statement 2. But we know theorem. Theorem 3 on monotonic sequences. A non-increasing sequence. A non-increasing sequence which is bounded below is convergent. This is a 3. From 1 to and 3, Sn x raised to n is non-increasing sequence. X raised to n is bounded below. Non-increasing sequence which is bounded below is convergent. Therefore, x raised to n is equal to 1 to infinity is convergent sequence. Therefore, limit convergent sequence. Therefore, we take limit n tends to infinity of x raised to n is equal to L, and we claim we have to show that L is equal to 0. Convergent sequence. Therefore, limit n tends to infinity of x to the power n is equal to L, say. L say L belongs to R. L is a real number. This is say 4. 4 रहेगा. Now x raised to n plus 1. Now x raised to n plus 1, n is equal to 1 to infinity, is subsequence of convergent sequence x raised to n is equal to 1 to infinity. But we know all subsequences of convergent sequence converge to the same limit. But we know all subsequences of convergent sequence converge to the same limit. Therefore, x raised to n plus 1, therefore the subsequence x raised to n plus 1, n is equal to 1 to infinity, converges to L. And we write limit n tends to infinity of x raised to n plus 1 is also equal to L. All subsequence of convergent sequence converge to the same limit. Therefore, subsequence x raised to n plus 1 converges to L. X raised to n plus 1, x to the power n plus 1 is equal to x raised to n into x. For all n belongs to I. Law of indices. By applying law of indices. Taking limit on both the sides as n tends to infinity, limit n tends to infinity of x to the power n plus 1 is equal to limit n tends to infinity of x raised to n into x is equal to, by using 4 and 5. By using above theorem, we write this as x times limit n tends to infinity of x raised to n. By 4 and 5. By 4 and 5. Or 5 and 4. Limit n tends to infinity of x raised to n plus 1 is equal to L. And x times limit n tends to infinity of x raised to n is equal to L. Limit n tends to infinity of x raised to n plus 1 is also equal to L. Therefore, L is equal to XL. That is, XL minus L is equal to 0. X minus 1 into L is equal to 0. X minus 1 into L is equal to 0. X minus 1 is not equal to 0, therefore L is equal to 0. Since 0 is less than x is less than 1, x is not equal to 1. X is not equal to 1, therefore L is equal to 0. Therefore, by 4, limit n tends to infinity of x raised to n is equal to 0. Therefore, sequence x raised to n is equal to 0, 1 to infinity, converges to 0, converges to 0. Proof of second result. Proof of second result. Since by hypothesis, one is less than x is less than infinity. 1 is less than x is less than infinity. That is x is greater than 1. X is greater than 1. By law of indices, x raised to n plus 1 is equal to x raised to n into x raised to 1. For all n belongs to I. For every n belongs to I. This x is greater than 1, therefore x raised to n plus 1 is greater than or equal to x raised to n. Since x is greater than 1. That is x raised to n is less than or equal to x raised to n plus 1 for all n belongs to I, for every positive integer n. If we put n is equal to 1, we obtain x is less than or equal to x square. If we put n is equal to 2, we obtain x square is less than or equal to x cube, less than or equal to and so on, less than or equal to x raised to n, less than or equal to x raised to n plus 1, less than or equal to and so on, and so on. Therefore, by definition of non-decreasing sequence Sn x raised to n is equal to 1 to infinity is non-decreasing sequence. This is a 6. X raised to n is equal to 1 to infinity is non-decreasing sequence. Suppose x raised to n is equal to 1 to infinity is bounded above. If possible, we suppose sequence x raised to n is equal to 1 to infinity is bounded above. This is a 7th statement. But we know theorem number 1 on monotonic sequences. Theorem number 1 on monotonic sequences, a non-decreasing sequence which is bounded above is convergent. Therefore, from 6, 7 and 8, this is 8. Therefore, from 6, 7 and 8, sequence x raised to n is equal to 1 to infinity is convergent. To say L. Therefore, limit n tends to infinity of x raised to n is equal to L. As in part first, we obtain x into L minus L is equal to 0. As in part first, we obtain x into L minus L is equal to 0. That is x minus 1 into L is equal to 0. Is equal to 0. And here x is L is equal to 0. X minus 1 is equal to 0 or L is equal to 0. L is equal to 0. And x is equal to 1. X is equal to 1. L is equal to 0 as in case first. Since x is strictly greater than 1, therefore x minus 1 is not equal to 0, x is not equal to 1. L is equal to 0. But x, by hypothesis, x is strictly greater than 1, therefore x raised to n is greater than 1, therefore x raised to n is greater than 1 for all n belongs to I. For every positive integer n, limit n tends to infinity of x raised to n is also greater than limit n tends to infinity of 1. Limit n tends to infinity of 1, which is equal to 1. That is, limit n tends to infinity of x raised to n is greater than 1. Greater than 1. This is say 8. Therefore, result 8 is contradiction to 9. Therefore, the result 8 is contradiction to result 9. Result 9. Therefore, our assumption is not true. Therefore, our assumption is not true. Not true. That is sequence x raised to n is equal to 1 to infinity is not bounded above. A non-decreasing sequence which is not bounded above diverges to infinity. But we know theorem 2, theorem 2 on monotonic sequences. A non-decreasing sequence, which is not bounded above diverges to infinity. Sequence x raised to n is equal to 1 to infinity is non-decreasing. Sequence x raised to n is not bounded above. Therefore, sequence x raised to n diverges to infinity. Therefore, from 6, 10 and 11. Therefore, from 6, 10 and 11, sequence x raised to n is equal to 1 to infinity, diverges to infinity. Hence the proof of part second. Proof of part third. Proof of part third. Since my hypothesis x is equal to 1, x is equal to 1. Therefore, x raised to n is equal to 1 raised to n for all n belongs to I, taking nth power on both the sides. 1 raised to n is 1, x raised to n is equal to 1 for all n belongs to I. Taking limit on both the sides, limit n tends to infinity of x raised to n is equal to limit n tends to infinity of 1 is equal to 1. That is limit n tends to infinity of x raised to n is equal to 1. Therefore, by definition of convergent sequence, sequence x raised to n is equal to 1 to infinity is convergent to 1. Hence the proof of theorem number 3.